Hello my dear students, welcome back to YouTube channel of Unique World Education Dubai. This is Faslur Rahman, Chemistry Faculty of Unique World Education. Hope all of you are fine and hope all of you are enjoying our sessions. In the last video, we were discussing about IUPAC nomenclature of coordination compounds. I hope you people are very perfect with the concept IUPAC nomenclature. Today we are going to discuss about a very important topic again from the same chapter, valence bond theory, VBT. Actually in this chapter, three important theories are there. One is Werner's theory, then valence bond theory and CFT, crystal field splitting theory. So right now we are going to learn valence bond theory in detail. Okay, so it's a very important part of this chapter, grade 12 syllabus. And definitely you can expect a 3 mark or 5 mark question from this one. And for those who are preparing JEE, NEET and all, definitely question will be there. Okay, so we can start. I hope all of you remember the nomenclature part very well, because without IUPAC nomenclature of coordination compounds, you can't complete this particular chapter. Okay, I hope you remember exactly about the ligands, type of ligand, then charges of ligands, density of ligand, everything. Okay, coming to valence bond theory, VBT, this exactly explains about the bonding pattern of a particular coordination compound. Like for example, how exactly a coordinate bond is made between a ligand and a central metal atom. All of you know that a ligand is a substance. A ligand is a substance or molecule which contain at least one lone pair of electron. Lone pair. So lone pair, all of you know, an extra pair of electron, right? So the ligand is sharing this particular lone pair of electron with central metal atom. That is actually called a coordinate bond. Okay, coordinate covalent bond. So if a complex is given, like if a coordination complex is given on the basis of valence bond theory, you have to say, you should know how to check the hybridization of the complex, hybridization of the central metal atom in the particular complex, like whether it is sp3 or whether it is d2sp3, like that. Okay, I'll teach you how to do that. Then you have to say whether the complex is paramagnetic or diamagnetic. Okay, so first hybridization, second magnetic behavior. So you can say whether it is paramagnetic or diamagnetic, and third one, you have to say whether the complex is inner complex or outer complex. Inner complex or outer complex, and you have to check whether the complex is low spin complex or high spin complex. Low spin complex or high spin complex. And the last one, that is magnetic moment of that particular complex. Okay, so very important. If a question is coming like this, for example, a compound is given, so explain on the basis of valence bond theory about the hybridization, about the magnetic behavior, about the spin of the complex, about the inner outer parameter, like that. So I will explain this particular topic using an example which will be very easy to catch up for you. So just wait. Okay. Yeah. So I'm just taking an example. CONH3 6 times 3 plus. Okay, this is the complex. Can you please name this complex, because we have studied the nomenclature in the last class, right? See, it's very simple, because the ligand is ammonia here, which is having neutral charge, which is 0 charge. So 6 ligands are there. So hexaamine hexaamine, and which is the central metal atom? Cobalt. Hexaamine cobalt. What is the oxidation state of the central metal? That is 3. Why? Because ammonia is 0 and this 3 plus is the charge of cobalt, central metal atom. So hexaamine cobalt 3. That is the name of this complex. So first you need to get the oxidation state of the central metal atom. So that is the first thing you have to do in this type of question. Okay. So oxidation number of the central metal atom is +3. Okay. So we have found that CO3 plus. Okay. Secondly, you have to write the electronic configuration. So I am again repeating this particular point, like you have to know the electronic configuration very well. So especially electronic configuration of elements from atomic numbers 21 to 30. 21 to 30 is very important for this particular chapter and D and F block chapter. I hope all of you remember the elements from 21 to 30. 21 to 30 means scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, so these atomic numbers are very important because in most of the coordination complexes, these elements, metals are coming as central metal atom. Clear? So what is the atomic number of cobalt? Atomic number of cobalt is 27. Atomic number of cobalt is 27. So we can first write the electronic configuration of cobalt. Electronic configuration of cobalt is argon till argon it is 18, right? Argon, then 4s2 3d7, 4s2 3d7, so 27. Okay, but we need the electronic configuration of CO3 plus. CO3 plus means what? 3 electrons are removed from cobalt. Okay, so it should be very careful while removing the electron. So you have to first remove this 2 electron because that is the outer shell. Okay, so 2 electrons from 4s and 1 electron from 3d will be removed. So what is the remaining configuration? That is just 3d6, argon 3d6. Clear? Now what you have to do means you have to show the box diagram for this particular configuration. Box diagram means orbital diagram, orbital box diagram. So we can check that CO3 plus, CO3 plus. So 3D. So you have to represent 3D orbitals. So all of you know that there are 5D orbitals. So you have to show 5 boxes. Okay, 5D orbitals. 1, 2, 3, 4. Okay, and you have to mark the orbitals as well. So 3D. Okay, how many electrons? 6 electrons. 1, 2, 3, 4, 5, 6. So in this way you have to arrange the electrons in orbitals. So you have studied these rules and all in grade 11. I hope all of you remember. And you can just mention the next coming orbitals as well because we need that for hybridization. So after 3D definitely it is 4s orbital. 4s. Okay, after 4s 4p. After 4s 4p. Okay, so now the orbitals are ready. Now what you have to do means you have to check how many ligands are there in that particular complex. So you can see from the complex how many ligands are there. How many ligands are there? 6 ligands are there. 6 ammonia ligands are there. Okay, so if 6 ammonia ligands are there, you know each ammonia ligand or each ammonia ligand is coming with a pair of electron. Okay, a ligand, what is a ligand? A ligand must contain at least a lone pair of electron. Ammonia is a monodendate ligand. So monodendate ligand means it can coordinate with central metal atom with one coordinate bond. So 6 ammonia ligand means 6 pair of electrons are coming. Clear? So the central metal atom should provide 6 free orbitals to accommodate the electrons of this incoming ligand. Okay. So 6 orbitals are needed. And one more very important thing, you have to check whether the ligand is strong field ligand or weak field ligand. So there are two types of ligands based on the field strength of ligands. If it is a strong field ligand, they will induce pairing. Induce pairing. Very important. Induce pairing means when this particular ligand is approaching the central metal atom, the unpaired electrons will get paired. Okay. If it is a weak field ligand, pairing will not happen. Okay. So ammonia is a strong field ligand. Ammonia is a strong field ligand. So definitely pairing will happen. So you can see 4 unpaired electrons are here. 4 unpaired electrons are here. So that unpaired electrons will get paired. Okay. So we can represent that. So you have to mention. So pairing. Okay. Due to strong field ligand. Pairing due to strong field ligand. So how is the pairing happening? Listen. 1, 2, 3, 4. 3D orbital again. So already one pair is there in that orbital and the 4 unpaired electrons will get paired. One pair here and one pair here. Okay. Then 4s orbital, then 4p orbital. Clear? Now 6 free orbitals are ready. We need 6 free orbitals. Why? Because 6 ligands are coming. Now what you have to do means you have to represent that orbitals which are going to hybridize. What is hybridization? Hybridization means intermixing of atomic orbitals to form a set of orbitals with same energy. You can see this is a d orbital and this is s orbital and this is p orbital. So different orbitals are intermixing to form a set of new orbitals with the same energy, or you can say degenerate orbitals. Clear? So you can mark the orbitals which are going to hybridize like this. Okay, this 2 orbitals, then this 1 orbital and this 3 orbitals. They are going to hybridize. Okay. So now in the next step you can just represent that orbitals in the combined form. Yeah. Okay. So hybridization. Clear? So how many orbitals are hybridized? 6 orbitals are hybridized. 6 orbitals are hybridized. 1, 2, 3, 4, 5. Okay. So all these orbitals will be having pairs of electron. Which pairs of electron? Pairs of electrons from ligand. Okay. So you can fill all the orbitals with the 2 electron. Fill all the orbitals with the 2 electron. Ready. And the very important thing, now we are going to check which is the hybridization pattern. Okay. These two orbitals are d orbitals, right? D orbitals. So how many d orbitals are participating? You can see 2 boxes. 2 boxes mean each box indicate 1 orbital. So 2 boxes mean 2 orbital. Which orbital? D orbital. So 2 d orbitals, that means you can write d2. Okay. And how many s orbital? 1 s orbital. So s. Okay. And how many p orbitals? 3 p orbitals. So p3. So what is hybridization? d2sp3. Very simple. Okay. So D2sp3 is the hybridization. D2sp3 is the hybridization. I hope all of you got it. Very important. In this manner you can check the hybridization. So what you have to do, I am repeating again. First, get the oxidation number of the central metal atom. Okay. Then write the electronic configuration of that central metal ion like this. Okay. And check whether the ligand is weak field ligand or strong field ligand. If strong field ligand, pairing will happen. So write the arrange the boxes according to pairing. After pairing, then check how many boxes, how many orbitals, free orbitals are required by checking the complex, how many ligands are there. Then do the corresponding hybridization. Okay. So this is the hybridization. And D2sp3. So I think this is clear. Now I am going to tell you what are the other parameters we need to check according to this one. Wait a minute, just wait. Yeah. Okay. Yeah. D2sp3 means the shape, the geometry of the complex is octahedral. Octahedral geometry. Okay, that is the first point. Octahedral geometry. And second point, I told you, so hybridization we have found out. Then geometry is ready. Then paramagnetic or diamagnetic. So you can see there is no unpaired electron here, and the previous page also, I think you remember, all the electrons are paired. Why? Because ammonia is a strong field ligand. How to check paramagnetism and diamagnetism means, see I am writing the point here, you can note. If unpaired electrons are present, that will be paramagnetic. If completely paired, no unpaired electron, that is diamagnetic. Okay, very important. So can you please tell me, this complex is paramagnetic or diamagnetic? No unpaired electron, completely paired. Okay, so this complex is diamagnetic. Okay. And the next point, the complex is inner complex or outer complex. See the hybridization, that is D2sp3, right? So this is based on, and this concept is only for octahedral complexes, inner or outer. If the hybridization pattern is D2sp3, you can see they are utilizing the inner d orbital, right? So D2sp3, that is inner orbital complex. Okay. If the hybridization is sp3d2, look, sp3d2. So this d2 is coming after sp3, right? That means they are utilizing outer d orbital. So if the hybridization is sp3d2, they will be outer complex, and if the hybridization is d2sp3, that will be inner complex. That's it. Okay. And what is the fourth one? That is low spin or high spin. Okay. High spin complexes means they contain more unpaired electrons. High spin. So you can see this complex is diamagnetic. Diamagnetic means what? Diamagnetic means completely paired, no unpaired electron. So that is a low spin complex. Okay. And finally, you can find out the magnetic moment. I hope all of you know that formula. We have one equation to find the magnetic moment. Magnetic moment mu, which is represented by mu. Mu is equal to root of n into n plus 2. Root of n into n plus 2. What is n? N is number of unpaired electrons. So regarding this complex, there is no unpaired electron. So what is the magnetic moment? Mu is equal to 0. Mu is equal to 0 because N is 0. Okay, that's it. So this is the idea of valence bond theory, and these are the 5 details you have to check with a complex. Okay, so what are the datas you need to get? First one, hybridization. Second one, geometry of the complex. Third one, inner or outer complex. Fourth one, paramagnetic or diamagnetic. And last one, magnetic moment. Okay, so I hope this topic is very clear, very perfect. It's a very important topic, a very important topic. I think the concept is very crystal clear. Okay, so first you have to get the electronic configuration, central metal atom, oxidation state of central metal atom. Based on that, you have to write the electronic configuration. Okay, then check the orbitals, how many orbitals are needed. Check whether the ligand is strong or weak. According to that, you can pair. Okay, then hybridize. Clear? Okay, so now I will give you one question as a homework. You can practice and you have to comment the correct answer in the comment box. Okay, so we can check how many of you are getting the correct answers. So I'm giving you one complex, so you have to tell me about that complex, whether the complex is diamagnetic, paramagnetic, whether the complex is inner or outer, or whether the complex is low spin or high spin. Many criteria, many parameters are there. Okay, so the complex is Ni NiCN4 NiCN4 2 minus NiCN4 2 minus. Okay, so do this as a practice work, homework, and you can come in the comment box with your answers. Okay, so what are the things you need to do? First, you can do the naming. Okay, then you can practice the nomenclature as well. So IUPAC name, then hybridization, geometry, inner or outer. Okay, then paramagnetic or diamagnetic, then magnetic moment, low spin or high spin. Okay, so I hope the topic is very clear, very perfect. If you have any doubts, you can ask in comment box, and you can comment like which topic you need for the next class. Okay, hope all of you are enjoying our sessions, and you can come with your suggestions like the topics you need, any difficult topic in any chapters, we can discuss that. Okay, okay, bye all, take care. Okay, bye.